Hi, high school chemistry teachers. I'm Kendra, creator of Chemed Solutions, and it's my mission to change the narrative of high school chemistry from yuck to yay by designing student and teacher materials that allow you to focus on what matters most, getting all your students to be confident and successful without the burden of using your personal time to do so. I support you by giving you my best proven tips vetted by thousands of students, parents, and case managers. So today's tip comes from our unit on the periodic table, focusing on ionization energy and explaining the trend. So I found that when my students are learning ionization energy, that they do their best to just memorize it and not take the time to understand it, which means that I need to spend the time in class helping them understand it over and over until they get it. And I found that acting out the trends is the best way to do so, and breaking down what the words mean. Even though they're words that we've used, I find that my students really don't understand what that means. So we start by breaking down ionization energy, the words. So we talk about, what does ionization mean? Well, let's find out what the root is. Ionize is in there. Well, ionize is to create an ion. And we talk about, well, how did you create ions? Or how do you get ions? What is an ion? And we talk about that. Well, that's when an atom either loses an electron, like metals, or gains an electron, like nonmetals. So we talk about that. Then we talk about energy. We say, well, what is energy? And even though they might not have had a physics class, we talk about, you expend a lot of energy, or you're tired because you're lacking energy because you did a lot of work. And so then we talk about, okay, well, energy is the amount of work required to do something. In this case, we're focusing on making ions. So energy to make ions. Then we go back to, well, how again do we make an ion? Oh, well, we add or remove an electron to make an ion. Okay, so let's talk about putting it together, ionization energy. Well, the energy required to turn an atom into an ion. And is it easy to do this? That means it takes less energy. And if it's difficult to do this, it takes more energy. From there, not only are we acting things out, but I also draw out my Bohr models with them. So lots of words here, but essentially what I'm doing is explaining how I focus on group one going down a column. So I say, okay, well, here's lithium, and then here is francium. And I draw out the Bohr models on the whiteboard or whatever I'm using. And we talk about how, okay, lithium, we have our 2 rings, my valence electron close to my nucleus here. Whereas francium, I have all of these rings of electrons, inner electrons, and then now I have my valence electron way out here. Okay, so much further away from my nucleus, plus all of these electrons kind of prevent my nucleus from attracting this outermost electrons. In addition, I also do a demonstration, either with a student or, depending upon the class, I'll do it. I'll take like a basketball, soccer ball, softball, volleyball, whatever, or hold something in my hand. And if I'm lithium, well, I'm holding that something pretty close to my body. So if somebody was trying to take that away from me, or if I have a student trying to take it away from another student, definitely harder to do so. However, with francium, if I have them be francium, well, now their arm is extended all the way out. That thing is being held right at the very end of their hand. Pretty easy, much easier to take that away from them. So we talk about, much easier, therefore less energy is required. So it means as I go down my group, right, I probably have drawn it like this on the board. As I've gone down my group, that means it takes less energy, therefore ionization energy decreases. From there, we talk about what happens if we go across the period. So again, I'm looking at my row with lithium, and I say, okay, from lithium to neon, again, if I'm going across, we talk about our size, because we've already talked about the atomic size trend by this point. And we know that neon is smaller than lithium. Additionally, we have the same number of rings. However, I have more protons in neon than lithium, so I'm able to hold these electrons in closer, and the attraction is greater there, so therefore they're held in tighter. And we also talk about how neon, noble gas, really, really happy, does not want to lose another electron, and so it is going to put up the biggest fight to try to take one away. Therefore, it's going to take so much energy to do so. So very, very high ionization energy here. So going across, we've increased our ionization energy. So this one, we're drawing pictures. The other one, we're acting out. And that really helps our students or my students understand what I'm talking about. So a lot of text there, but that's what I'm saying. And then we would do some practice. So I'd say, okay, this one or that one. And then we would either, if it's in a group, the same group, we would act it out. If it's in the same row or period, I would have them draw it. Again, look at, if we're closest to a noble gas, we're not going to want to lose those valence electrons. To never miss a weekly teacher toolkit tip and get access to a PDF copy of both the teacher and student versions of this. So I have a student version as well that you could use in class here. So you get that. You can sign up for my weekly newsletter at chemedsolutions.com/chemguide. And in addition to teacher toolkits, when you sign up, I have some thank you gifts for you, including a high school chemistry course outline, pacing guide, so you know that you're on track, unit checklists, and my personal teacher planner to keep yourself organized, less stressed, and enjoying life. So with all of that, happy sciencing!